There is a small drawing every child makes, somewhere around the age of 6 or 7, the moment somebody hands them a piece of paper and tells them to draw a planet. They draw a circle. Then they draw an oval through the circle. The oval is the rings. The circle is Saturn. That single image, more than any photograph, more than any telescope view, is the universal symbol of a planet inside the human imagination. Even people who have never thought about astronomy in their lives can recognize Saturn from across a room. Among all the worlds in our solar system, Saturn is the one we agreed on, the one that does not need a label. Now imagine looking through a telescope on a clear night and finding that the rings are gone. Not destroyed, not knocked out of orbit, not damaged in some cosmic accident, just gone. The most recognizable feature of the most recognizable planet in our sky has, for that one night, simply vanished from view, leaving behind a bare gold marble that looks almost embarrassed to be seen without its crown. That is what astronomers around the world saw on the 23rd of March, 2025. Saturn undressed. The rings did not actually disappear. They are still there. They are still in orbit. They are still flowing slowly around the planet exactly the way they have been for as long as humans have been pointing telescopes at the sky. What changed was the angle. As Saturn and Earth move along their respective orbits, the tilt between them shifts year by year, and every 15 years or so, our viewing angle rotates until we are looking at the rings exactly edge-on, the way you might look at a piece of paper held perfectly sideways. From that perspective, the entire structure becomes invisible. Because the rings of Saturn, the most famous object in our solar system, the object whose silhouette every child knows, are in some places only 10 meters thick. Thinner than the height of a single house, spread across a structure wider than the distance between Earth and our own moon. This is the kind of fact that does not stay still in the brain. You hear it once, and your imagination tries to push back. Surely a structure that big has to be more substantial than that. Surely something that grand cannot be that delicate. But the geometry is real. The thinness is real. Saturn's rings are essentially a sheet of frozen water held flat by the gravity of the planet, and most of that sheet is somewhere between 30 and 300 feet from top to bottom. By cosmic standards, by any standard, that is paper. That is foil. That is breath on a window. So when the geometry tilts and we end up looking straight down the edge of that foil, the rings simply stop being visible to us. They become a hairline that even our best telescopes struggle to resolve. And on the night of the 23rd of March, 2025, when the alignment fell perfectly into place, Saturn returned to looking like the small, unadorned ball that the rest of the gas giants resemble. Just for a moment. Just long enough for the photographers and the planetary scientists and the people who care about these things to notice that the most famous planet in human history can hide its most famous feature with a simple turn of the head. It is a small thing. It is also a useful thing. Because what happened that night is a metaphor for what has been happening to Saturn in the data, in the science, in the slow, patient archives of every spacecraft we have ever sent to look at it. Saturn has been hiding things in plain sight, and in the past 3 years, as researchers have gone back into the records left behind by a dead spacecraft and looked at them with new eyes, the list of things Saturn has been hiding has grown into something genuinely uncomfortable. The rings, it turns out, are not nearly as old as anyone believed. The moons have almost doubled. One of the most promising places for life in the entire solar system may have just lost its underground ocean. The chemistry on the surface of Saturn's largest moon is doing things that a first-year chemistry textbook says should be impossible. And on the planet's north pole, above a six-sided storm system that nobody can explain, the James Webb Space Telescope has just photographed structures that nobody predicted, in layers of the atmosphere that nobody knew could hold them. Saturn is not a settled world. Saturn is the scene of a recent accident. And tonight, slowly, gently, in the quiet way that only a sleeping mind can really receive cosmic news, we are going to walk through every reversal that has happened in the past 3 years and try to understand what kind of planet this actually is and what we have all been quietly mistaken about for the past 400 years. If you find your mind drifting as we go, that is not a problem. Drift is the right state for this kind of journey. The universe is patient. The story is patient. And if cosmic mysteries are the kind of thing that pull you in and keep you up too late on too many nights, you already know what subscribing here will do. We will be back, slowly, with more of these. The dark above us is full of revisions waiting to happen. For now, let us start with the rings. But before we get to what the rings actually are, take a moment to picture what humans have actually been doing with Saturn for the past 4 centuries. Because the story of how we came to know this planet is, in its own way, just as strange as the story of what we are still learning. In the autumn of 1610, the Italian astronomer Galileo Galilei pointed one of the first working telescopes ever built at Saturn and saw something he could not understand. The instrument he was using had a magnification of about 30 times. By modern standards, that is roughly the power of a decent pair of binoculars. By the standards of his day, it was the most powerful tool human eyes had ever had access to. Through it, Galileo could resolve the moons of Jupiter, the phases of Venus, the craters of our own moon. He could see things no human had ever seen before. And when he turned the instrument on Saturn, he wrote in a letter to a colleague that he had observed not one body, but 3. The planet, he believed, was flanked by 2 smaller companions, one on each side, hugging close to it. He drew a small sketch in his notebook. 3 dots in a row. 2 years later, Galileo turned the telescope on Saturn again, expecting to see the same thing he had seen before. The companions were gone. The planet was alone. He wrote with a kind of bewildered grief that survives in his letters to this day, that Saturn must have devoured his own children. He used the imagery of the Greek Titan, the figure who, in mythology, ate his offspring to prevent them from overthrowing him. The astronomy and the mythology blurred together for a moment in his confusion. Where the companions had been in his earlier sketches, there was now nothing. What Galileo had unknowingly observed was the same edge on alignment that astronomers saw in March of 2025. The rings, viewed from the wrong angle, had simply disappeared. He had no way of knowing this. The concept of rings around a planet did not yet exist as a category in human thought. The geometry of the system had not yet been worked out by anybody. He was looking at one of the most famous structures in our solar system, without any idea what it was, and watching it vanish and trying to make sense of it through the only frameworks his time had to offer, which were the frameworks of myth. It would take another half-century before someone got it right. In 1655, the Dutch astronomer Christian Huygens, using a much-improved telescope of his own design, finally observed Saturn clearly enough to realize that the strange shapes Galileo had drawn were the appearance of a single thin disk surrounding the planet, tilted at an angle, sometimes visible from one face, sometimes seen edge-on. The companions were not companions at all. They were the 2 visible edges of a single ring, presented from a particular angle of view. Huygens, with characteristic precision, published his finding in a coded anagram that nobody could decipher until he revealed the solution 3 years later. He had wanted to be sure of the result before letting other astronomers race ahead of him. In 1743, the French-Italian astronomer Giovanni Domenico Cassini, after whom the modern spacecraft was named, observed that what Huygens had described as a single ring was actually 2 distinct rings, separated by a gap that bears his name to this day. The Cassini division, a dark line visible in any modern photograph of the planet, that splits the bright outer ring from the slightly less bright inner ring. The gap itself is a region where gravitational interactions with one of Saturn's small moons have cleared away most of the ice particles, leaving an apparent emptiness in the middle of the ring system. Each of these realizations was, in its own moment, a small revolution. Each of them rewrote what humans thought they understood about the most famous planet in the sky. And each of them happened only because someone, somewhere, looked again, more carefully, with better tools or with fresher questions, at the same body that had been hanging in the same place all along. This is the rhythm, the pattern, the thing that this whole story keeps repeating. Saturn does not change. Our ability to read Saturn changes, and every few generations, we discover that the version of the planet we had agreed on was incomplete. The Saturn that Galileo died believing in was missing the rings as a coherent structure. The Saturn that Huygens died believing in was missing the gaps. The Saturn that the original Cassini died believing in was missing the moons we now know are there. The Saturn that the Voyager teams of the 1970s and 80s died believing in was missing the geological activity of Enceladus, the chemistry of Titan, the precise structure of the rings, the existence of the polar hexagon, and almost everything else we have learned in the past 40 years. Every previous generation of humans had a Saturn that was, in some basic way, wrong. And the version we have today is, almost certainly, also wrong, in ways we will not understand until somebody comes along after us with better tools, looking again. That is a humbling thought. It is also, in its own way, a hopeful one. The universe is not finished giving us things. The work is not done. The rings of Saturn that you can look at tonight in any decent telescope are exactly the same rings that Galileo saw 400 years ago. They have not moved. They have not changed. What changes is us looking at them. And every century or so, we develop a new way of looking that makes the old rings show us something new. For most of the last 400 years, since Galileo first pointed his telescope at Saturn in 1610 and saw something he could not quite resolve, the rings of this planet have been treated as a permanent fixture, a structure as old as the planet itself, a leftover from the same disk of gas and dust that built Saturn out of the early solar system roughly 4.5 billion years ago. A fossil of the cosmic dawn, older than anything alive on Earth, older than Earth itself in a sense, because Earth was still being assembled at the same time. The rings, in that picture, are something you could point to and say, those are ancient. Those have always been there. Those will outlast us. That picture is gone now. The best evidence available to science today points to the rings being no more than 100 million years old, possibly far less. A figure that sounds enormous when you first hear it, and then collapses the moment you put it next to the actual age of the planet. Saturn is roughly 45 times older than its own rings. The crown is brand new compared to the head wearing it. To get a feel for how strange that is, consider what was happening on Earth during the time the rings first formed. The dinosaurs were already old. They had already been ruling our planet for tens of millions of years. They were not the first reptiles, not the first vertebrates, not the first complex life. The rings of Saturn arrived in our solar system after fish had already crawled out of the water on Earth, after forests had already covered our continents, after our own world had already been through ice ages and extinctions and entire chapters of biological history. Saturn's rings are younger than the first trees. Saturn's rings are younger than the dinosaurs. The evidence for this came from the Cassini spacecraft, and to understand the evidence, it is worth taking a moment to understand the spacecraft itself. Because Cassini was not just an instrument. Cassini was, in some real sense, a 30-year human achievement. The kind of project that begins with a few sketches on a whiteboard in a planning meeting and ends with a robot the size of a school bus screaming through the atmosphere of a planet a billion miles away. The mission was conceived in the 1980s as a joint project between the American Space Agency, NASA, the European Space Agency, and the Italian Space Agency. The idea was ambitious. Send a single large spacecraft to Saturn. Have it carry a smaller probe that could detach and parachute to the surface of Titan. Have the main spacecraft remain in orbit around Saturn for years afterward, studying the planet, the rings, and the moons in unprecedented detail. The whole project took 15 years to design and build. Engineers from dozens of countries contributed components. Scientists from hundreds of institutions argued for years about which instruments would fly and which would not. The total cost, by the time the spacecraft launched, was somewhere around $3.5 billion. Cassini left Earth in October of 1997 on top of a Titan rocket from Cape Canaveral. The journey to Saturn would take 7 years. To get there, the spacecraft did not fly directly. It could not. The fuel required for a direct trajectory would have been enormous, beyond anything the rocket could carry. Instead, Cassini used a technique called gravity assist, in which a spacecraft swings close to a planet and uses the planet's gravitational field to gain or lose energy without burning any fuel. Cassini swung past Venus twice, then past Earth, then past Jupiter, picking up speed at each encounter until it finally had enough velocity to reach the outer solar system. The trajectory looked on paper like a slow loop drawn through the inner planets and then flung outward toward Saturn. When the spacecraft finally arrived in 2004, it carried out the most precise orbital insertion ever attempted. To enter orbit around Saturn, Cassini had to fire its main engine for 96 minutes, slowing itself down enough to be captured by the planet's gravity. The maneuver was risky. If the engine failed, the spacecraft would simply fly past Saturn and continue out into the dark, unrecoverable. If the engine fired for too long or too short a time, the orbit would be wrong and the mission would be partially compromised. Engineers on Earth could not control the firing in real time because the radio signal between Earth and Saturn takes more than an hour to travel each way. Cassini had to perform the maneuver autonomously, following pre-programmed instructions that had been uploaded weeks in advance, while the team on the ground waited and watched and held their breath. The maneuver worked. Cassini entered orbit, and then, 6 months later, in January of 2005, it released the Huygens probe. Huygens was the smaller spacecraft, named after the same Christian Huygens, who first identified the rings as a coherent structure 3.5 centuries earlier. It was about 9 feet across, roughly the shape of a wok, packed with instruments designed to study Titan's atmosphere and surface as the probe descended through the orange haze. After release from Cassini, Huygens coasted toward Titan for 3 weeks. On the 14th of January, 2005, It entered the moon's atmosphere at 14,000 miles per hour, deployed a series of parachutes, and began the slow descent through the thick nitrogen veil that had hidden Titan's surface from human eyes for centuries. The descent took 2.5 hours. During that time, Huygens transmitted data continuously back to the orbiting Cassini, which relayed it to Earth. Photographs began arriving in real time as the probe sank lower and lower through the atmosphere. The first images showed an orange, murky landscape that nobody had quite expected. Channels carved by liquid hydrocarbon rains, dark plains that looked like dry lake beds, pebble-like rocks in the distance. The probe finally touched down on a relatively flat surface, dampened by recent methane drizzle, and continued to transmit data for another 70 minutes before its batteries died, and Titan reclaimed it for the cold. The Huygens landing remains, to this day, the most distant landing humans have ever achieved. No spacecraft has ever set down further from Earth. The probe sits, presumably still in one piece, on the frozen surface of Titan, slowly being covered by whatever atmospheric chemistry continues to fall there. It is a small monument, an engineering achievement that may never be repeated within a generation, sitting in the dark on a moon 1 billion miles away. Cassini, meanwhile, kept going. The spacecraft was originally scheduled for a 4-year primary mission. When the 4 years ended, the spacecraft was healthy, and the science team requested an extension. The extension was granted. When that one ended, another was granted, then another. By the time the mission finally ended, Cassini had been at Saturn for 13 years, made nearly 300 orbits of the planet, performed dozens of close flybys of Titan and Enceladus and the smaller moons, and collected an archive of data so vast that scientists are still, today, 8 years after the mission ended, finding things in it that nobody noticed at the time. The end of the mission was deliberate. By 2017, Cassini was running low on fuel. The team had a choice. They could leave the spacecraft to drift forever, eventually possibly crashing into one of Saturn's moons. Or they could end the mission on their own terms, in a way that would protect the moons from any contamination by Earth bacteria that might have hitched a ride on the spacecraft 30 years earlier. The team chose the second option. They called it the grand finale. In the final months before the planned destruction, Cassini was sent on its boldest set of maneuvers ever. 22 orbital dives, each one threading the spacecraft through a narrow corridor between the cloud tops of Saturn and the inner edge of the rings, a corridor only about 1,200 miles wide. Every dive collected data nobody had ever collected before. The dives passed close enough to the planet's atmosphere to sample its composition directly. The spacecraft measured magnetic fields, gravitational variations, atmospheric chemistry. It took photographs of the rings from angles no probe had ever been at. And on the 15th of September, 2017, on its final dive, Cassini was sent into the upper atmosphere of Saturn itself, where it broke apart and was vaporized in a brief flash of light that nobody on Earth could see, ending its life as a part of the planet it had spent 13 years studying. The reason the spacecraft was destroyed deliberately, instead of being parked in some quiet orbit, was a quiet one. Enceladus had become so important to the science of finding life elsewhere that the team did not want to risk Cassini eventually crashing into it and contaminating the subsurface ocean with Earth bacteria. The spacecraft was sacrificed to protect the very moons it had taught us about. It is one of the strangest endings in the history of space exploration. A probe destroyed deliberately because the world it had discovered was too precious to risk. In the final months of its life, during those 22 grand finale dives, Cassini did something no spacecraft had ever done before. It threaded itself through the gap between Saturn and the rings, which gave its instruments their first ever chance to measure the gravity of the rings directly. And what they found was the answer to a question that had been quietly hanging over astronomy for decades. The rings, it turned out, were not what anyone thought they were. In the final months of its life, Cassini was sent into a series of maneuvers nobody had ever attempted before. 22 orbital dives, each one threading the spacecraft through a narrow corridor between the cloud tops of Saturn and the inner edge of the rings. The corridor was only about 1,200 miles wide, which by the standards of spacecraft navigation is a very tight squeeze. Every time Cassini made the dive, the gravity of the planet pulled on it from one side, and the gravity of the rings pulled on it from the other. By measuring how those two forces tugged the spacecraft off its expected path, the team back on Earth could weigh the rings directly for the very first time. The answer surprised them. The rings turned out to be lighter than anyone expected, and in cosmic mechanics, a light ring system is almost always a young ring system. Older rings should have collected mass over time as passing debris fell into them and stuck, the way snow collects on a windowsill that has been left open for a long winter. The rings of Saturn have not had time to collect that mass. They are, in this measurement, much closer to the snowfall of last week than to the geological history of a planet. The ice itself told the same story. Cassini's cameras and spectrometers studied the reflectivity of the particles in the main rings and found them startlingly bright. Almost too bright. Over geological time spans, micrometeoroids rain down on ring material the way dust drifts onto a high shelf. The longer the rings are around, the dirtier they should look, coated by a thin veneer of dark mineral particles delivered slowly across the millennia. The main rings of Saturn have almost none of that coating. Whatever made them recently. And whatever they are leaving. Saturn is slowly eating its own rings. The process has a soft name: ring rain. The mechanics of it work like this. Stray ultraviolet light from the sun, combined with the constant impact of micrometeoroids, gives some of the ice particles in the rings a small electric charge. Once a particle is charged, it becomes vulnerable to Saturn's enormous magnetic field, which grabs the particle, tilts it out of its orbit, and guides it down into the upper atmosphere of the planet, where it vaporizes. From the measurements Cassini collected during its final dives, the amount of water raining out of the rings and into Saturn every second is enough to fill an Olympic swimming pool roughly every half hour. Saturn is, in the most literal sense, drinking its own rings. Project that loss forward across cosmic time, and the math becomes uncomfortable. Estimates of how long the rings have left to live range from around 15 million years to about 400 million years. The exact number is still being argued by the people who care most about these things, and the argument has not been resolved. The direction is not in dispute. The rings are leaving. They are not a permanent feature of the planet. They are a temporary structure caught in the middle of a slow disappearance, and we are simply lucky enough to be alive during the brief geological window when they happen to be visible. That brings us to the question that nobody asked very seriously before, and that everyone is asking now. If the rings are young, where did they come from? The leading hypothesis, still openly described as a hypothesis by the people who study it, is that one of Saturn's own moons died to make them. Specifically, a mid-sized icy moon, somewhere in the past 100 million years, was torn apart by a violent event. Maybe a passing comet struck it at exactly the wrong angle and at the wrong speed. Maybe the moon's orbit decayed inward over time until tidal forces from Saturn ripped it apart. Maybe a collision with another, smaller body started a chain reaction that nobody can model in detail. Whatever the trigger was, the moon shattered. The fragments, made mostly of water ice with traces of rock, spread out into a flat disk around the planet. And that disk, ground down by collisions with itself across the millennia that followed, eventually settled into the structure we now call the rings. If that is what happened, then everything on Earth that has ever drawn a picture of Saturn has been drawing the gravestone of a moon. The most famous feature of our solar system is, possibly, the dispersed corpse of one of Saturn's own children. A funeral pyre suspended in orbit, glowing white in the sunlight, slowly raining itself down into the planet that killed it. It is a strange thing to sit with. A planet that briefly wears rings, a structure that Galileo and Cassini and every astronomer who ever lived just happened to catch in the middle of a short, bright life. And the more we look at the rest of the system around Saturn, the more this story keeps repeating. The rings are not the only thing in this neighborhood that turned out to be the wreckage of something that once was. Far above Earth, on the summit of Mauna Kea, the dormant volcano in Hawaii that rises more than 4 kilometers above the surrounding ocean, there is a telescope called the Canada-France-Hawaii Telescope. It is not the most famous instrument in astronomy. It does not get the publicity that the bigger telescopes attract, the ones photographed for magazine covers and documentary opening sequences. It is a working observatory, a tool, a quiet machine pointed at quiet patches of sky. Between 2019 and 2021, the people running it spent 3 years staring at the patches of sky that surrounded Saturn. They were not looking for anything famous. They were looking for moons. The team running the observation was led by Edward Ashton at Academia Sinica in Taiwan, working with Brett Gladman at the University of British Columbia. Their goal was to find moons too small and too dim to show up in any single photograph. To do that, they used a technique that sounds almost like cheating, but is in fact one of the most powerful methods in modern observational astronomy. You take the telescope. You point it not at the stars themselves, but at the predicted path of whatever faint object you are hunting for. You move the telescope at exactly the speed and direction that object should be moving across the sky. Then you take photograph after photograph after photograph of the same patch of sky. Each individual frame is too noisy to show the object. The signal is buried under random static, the unavoidable noise of any imaging system. But when you stack the frames on top of each other, with the telescope's tracking holding the predicted object in the same place across every image, the random noise begins to average itself out. The signal, which is always in the same position relative to the tracking, slowly emerges from the static like something developing in a darkroom tray. Faces appear out of the gray. Objects materialize that no single photograph could have ever shown. This technique has a formal name, shift and stack, sometimes called digital tracking. What it does in practice is allow astronomers to find objects that are, in effect, far below the detection threshold of any individual exposure. It pulls the cosmos out of the noise. Between 2019 and 2021, Ashton and Gladman's team used this method to pull dozens of candidate moons out of the dark around Saturn. In 2023, they returned to the same patches of sky 3 months running, to confirm that the candidates were real and to track their orbits with enough precision to be sure they were genuinely orbiting Saturn rather than drifting through. On the 11th of March, 2025, the International Astronomical Union, which is the official body that recognizes new objects in our solar system, made the discoveries official. 128 new moons of Saturn, confirmed, catalogued, all on the same day. Saturn's known moon count went from 146 to 274 overnight. More moons than every other planet in our solar system combined. More moons than Jupiter, Uranus, Neptune, Mars, and Earth put together, and then some. None of the new moons is large. Every single one of the 128 is what astronomers call an irregular moon. Small, typically just 1 to 3 kilometers across, the size of a city neighborhood rather than a world. Traveling on tilted, looping, often retrograde orbits that move backwards against the direction of Saturn's own rotation. They are not the kind of moons that formed alongside Saturn out of the original disk of gas and dust that gave birth to the planet. Those moons, the regular ones, follow neat circular paths in the same direction as Saturn's spin, the way debris in a centrifuge settles into a clean pattern. The irregular moons do not. They are foreigners, captured fragments. Debris that was wandering through the outer solar system at some point in the past, came too close to Saturn, fell into its gravity, and never left. The orbits cluster. This is the part that turned out to matter. Most of the new moons are not scattered randomly through the space around Saturn. They are piled up in a particular region of orbital space, around a group called the Mundilfari subgroup, named after a moon already known to inhabit that part of the sky. And the clustering itself is the clue. In the asteroid belt, far closer to home, astronomers have been studying the same kind of phenomenon for over 100 years. Groups of asteroids called Hirayama families, first identified by the Japanese astronomer Kiyotsugu Hirayama in 1918, are tightly clustered swarms of small bodies that share suspiciously similar orbits. The interpretation, which has held up for a century, is that each Hirayama family represents the shattered remains of a single parent body. Some larger asteroid, long ago, was hit hard enough to break apart, the fragments scattered, but the orbital memory of their shared origin survived in the statistics. Even today, you can identify the family members by looking at the family resemblance in their orbital parameters, the same way you might identify siblings in a crowd by the way they all hold their shoulders. The Mundilfari subgroup around Saturn is the same phenomenon, scaled up, moved outward, and applied to moons instead of asteroids. The interpretation is the same. The cluster is the wreckage of a single object that broke apart, and the broken pieces are still flying together because they have not yet had time to drift apart. Brett Gladman has been clear about what this means. If the moons in the Mundilfari group were billions of years old, they would not still exist in their current form. At their sizes and densities, they would have collided with each other across geological time and ground themselves down into smaller and smaller pieces, eventually becoming dust. The fact that 128 of them are still flying around Saturn, tightly grouped in formation, tells you they have not been around for very long. The collision that made them happened sometime in the past 100 million years, possibly more recently than that. Read that sentence again, slowly. A collision in the recent past. A larger moon shattered into pieces inside the same 100 million year window during which the rings of Saturn formed. The dating overlaps. The pattern repeats. Saturn keeps handing us, in different forms, the same story. A story of a moon that died. A planet that built its crown out of the corpse of one of its children. And then, separately, possibly unrelated, but maybe not, another moon dying somewhere else in the system, scattering its fragments into a swarm that we have only just begun to catalog. It is not lost on the scientists who study these things that two of the most striking features of the Saturn system, the rings and the irregular moons, both seem to be the products of relatively recent destruction. Saturn looks calm. Saturn looks like a settled world. Saturn's photographs are some of the most peaceful images astronomy has ever produced. But underneath that calm, the system has been chaotic in ways that we are only just beginning to read. This is the frame to carry into the next part of the journey. Because in December of 2025, one of the most promising places for life in the entire solar system, a moon that everyone thought they understood, turned out to be something nobody had quite imagined before. And the change in our understanding came not from a new spacecraft, not from a new mission, but from a researcher going back into data that had been sitting quietly in an archive for almost 20 years. If we are still walking together at this point in the journey, take a slow breath. We have only just begun. The strangest things Saturn is hiding live not on the planet itself, but on the moons that orbit it. And the strangest moon of all is one whose surface is colder than anywhere on Earth has ever been, and whose chemistry has been quietly breaking laws that humans wrote down 150 years ago. For almost 2 decades, Titan was an ocean world. Every scientist who studied it agreed on that. The largest moon of Saturn, a body bigger than the planet Mercury, wrapped in an orange nitrogen atmosphere thicker than Earth's own, with rivers and lakes and seas of liquid methane carving channels across its frozen surface. And underneath all of that, hidden beneath a shell of water ice somewhere around 50 miles deep, a global ocean of liquid water. Salty, probably warm, stretching all the way around the moon, potentially habitable. One of the most exciting candidates in the entire solar system for the question of whether life exists somewhere other than here. That picture came from Cassini. Beginning in 2006 and continuing across multiple targeted flybys over the rest of the mission, the spacecraft gathered the gravitational data that scientists needed to figure out what was inside Titan. The key measurement they were after has a beautiful name: the tidal love number. It is a single dimensionless quantity that describes how much a body deforms when an external gravitational force tries to squeeze it. A perfectly rigid, completely solid object has a love number close to 0. It does not flex. A body with a substantial liquid layer inside has a love number much closer to 1, because the solid outer shell can shift and deform on top of the liquid layer like a skin sliding on water. In 2008, the Cassini spacecraft made the first of 10 close flybys of Titan, each one designed to measure exactly how much the moon was deforming as it swung around Saturn on its orbital path. The method is, in its own way, beautiful. As Titan moves around Saturn, the gravity of the planet pulls harder on the near side of the moon than on the far side. That difference squeezes Titan into a slight football shape, with the long axis of the football pointed back toward Saturn. If Titan were a solid ball of rock and ice all the way through, the squeezing would barely move anything. The moon would flex by a few inches at most. But if Titan had a liquid layer inside, the flexing would be much larger, because the solid outer shell could shift around on top of the underground ocean the way ice on a frozen pond shifts when you press on it. To measure the flex, the Cassini team watched what happened to the radio signal coming back from the spacecraft during each flyby. Tiny changes in the signal's frequency, down to fractions of a single hertz, told them exactly how much the gravitational pull from Titan and Saturn had bent the spacecraft's path. From that bending, they could calculate how much Titan itself had deformed. The math is elegant. The method is precise. And in the years of analysis that followed, culminating in a landmark paper published in the journal Science in 2012 by Luciano Ies and his colleagues, the numbers came back surprisingly large. Titan was flexing like something with liquid inside. Quite a lot of liquid. The team concluded that there had to be an ocean underneath the ice. And for the next 17 years, that conclusion was the settled answer. Textbooks were updated, documentaries were filmed, mission proposals were written, including one for a future spacecraft that might one day drill through the ice and sample what was underneath. The picture was clear. Titan was an ocean world. On the 17th of December, 2025, a paper published in the journal Nature took that picture apart. The new study, led by Luigi Petrica and Baptiste Journeau at NASA's Jet Propulsion Laboratory, revisited the original Cassini radio data using improved modeling techniques that did not exist when the original analysis was performed in 2012. They went back to the raw signals and asked a question that the original team had not closely examined. How long does it take for Titan to respond to Saturn's pull? When Saturn's gravity reaches its peak strength on Titan's near side, does the flex in Titan happen instantly? Or does it lag behind? In a true global ocean world, the response is almost instant. Water under an ice shell moves freely. The shell above it floats and shifts on top of that water with very little resistance. If the moon is being squeezed, it squeezes immediately. The lag time between cause and effect is short enough that it might as well not exist. The new analysis found a lag of roughly 15 hours. Read that number again. 15 hours between when Saturn's gravity reaches its peak pull on Titan and when Titan's actual flex peaks in response. 15 hours is not what an ocean does. 15 hours is what slush does. Ice that is close to melting but not actually liquid. Thick, sticky, resisting the gravitational pull and yielding only slowly, the way you might stir cold honey instead of water. The mechanical signature of slush is fundamentally different from the mechanical signature of free-flowing liquid, and Titan's signature, in this new reading, looks more like the former than the latter. The picture Petrica and Journeau are now proposing for the inside of Titan looks very different from the one that has been on textbook pages since the original analysis. In the new picture, there is an outer shell of harder ice, around 100 miles deep. Beneath that, there is not a clean global ocean, but a layer of icy slush, roughly 230 miles thick, neither fully solid nor fully liquid. Running through that slush, there are scattered pockets of warm water, kept just above freezing by heat rising from deeper inside the moon. The slush is interrupted by these pockets, the way a frozen lake is interrupted by patches of meltwater on a warm spring day. There may still be liquid water inside Titan, but there is not necessarily an ocean. There may instead be a vast, slow layer of partly frozen mush, with isolated reservoirs of true liquid scattered through it like raisins in oatmeal. Not everyone is convinced. Luciano Es, the lead author of the original 2012 paper that first proposed Titan's ocean, has been quoted saying the new analysis is interesting and will push the field forward, but that the available evidence is not yet enough to remove Titan from the list of ocean worlds. The disagreement is still active. Both teams are working from the same Cassini data. Both teams are trustworthy. The difference is in how the physical models interpret that data, and resolving the dispute may require a future mission with instruments designed specifically to distinguish between these competing pictures of what Titan's interior is made of. But here's the important thing to hold on to, before we lose it in the noise of who is right and who is wrong. The search for life on Titan has not been canceled by this finding. It has been relocated. A global ocean is one kind of place where life could possibly exist. A slushy layer full of warm water pockets near a rocky core, with chemistry, with heat, with mineral surfaces, is another kind of place. Possibly a stranger one. Possibly, in some ways, a more interesting one. Life on Earth is fundamentally a chemistry that happens at interfaces, and a slush layer full of pockets and boundaries is, if anything, more interface-heavy than a single open ocean. The question of life on Titan has not become simpler, it has become weirder. And whatever Titan actually is, it is now stranger than the version we thought we understood. That strangeness is not confined to the inside of the moon. On the surface of Titan, in the freezing cold, under the orange haze of the thick nitrogen atmosphere, something is happening that by the rules of chemistry as humans have written them down, should not be possible. What happens to chemistry in a place colder than anywhere on Earth has ever been? Titan is that place. The temperature on its surface sits around -290 degrees Fahrenheit. At those temperatures, water is not a liquid. Water is a rock. Water ice on Titan is harder than concrete, harder than most of the minerals you can find on Earth, harder than anything most people have ever encountered. The lakes and seas on Titan are not made of water. They are made of liquid methane and liquid ethane, the same hydrocarbon fuels that humans burn on Earth, kept in their liquid state by the incredible cold and by the pressure of the thick nitrogen atmosphere overhead. In 2015, Cassini looked down through that orange atmosphere using its infrared instruments. The atmosphere of Titan is opaque to visible light. Through an ordinary camera, the surface looks like nothing, just orange haze. For most of the mission, scientists could only guess at what was hiding under that veil. But the infrared cuts straight through. What the camera saw in the near-infrared wavelengths was a world of dark, mirror-flat lakes, winding river channels carved by hydrocarbon rains, and the outlines of vast dunes made not of sand, but of tarry organic dust that had drifted down from the upper atmosphere and piled up in the wind. It was the clearest look anyone had ever had at the surface of Titan. And in those images, the team noticed features they could not fully explain. Solid material at the edges of the lakes, bright deposits in places where the chemistry, on paper, should not have allowed anything unusual to form. There was something out there, sitting in the cold under the orange sky, that did not match what the textbook said should be there. The textbook in question is one of the oldest in chemistry. The rule it contains is taught in the first weeks of any introductory course. The rule says, like dissolves like. Polar molecules, the ones with an uneven distribution of electrical charge across them, mix well with other polar molecules. Nonpolar molecules, the ones with a more even distribution of charge, mix well with other nonpolar molecules. But polar and nonpolar molecules do not mix with each other. Oil and water, the classic example, do not mix because water is strongly polar and oil is not. The two kinds of substances slide past each other and refuse to combine, no matter how vigorously you shake them. This rule has been the foundation of chemistry for over 150 years. It has held up across countless experiments. It has been tested and confirmed in every corner of the periodic table. It is not a guideline. It is a law. Titan breaks it. In July of 2025, a team led by Fernanda Iglesia Ruiz and Martin Rahm at Chalmers University of Technology in Sweden, working with Morgan Cable and Robert Hodis at NASA's Jet Propulsion Laboratory, published a paper in the Proceedings of the National Academy of Sciences that did something unusual. They took the Cassini measurements of Titan's surface, combined them with thousands of computer simulations, and asked a question that had not been asked clearly before. Could the materials sitting on Titan's surface be forming crystal structures that, by every textbook rule, should not be able to exist? The molecule they focused on was hydrogen cyanide. Hydrogen cyanide is everywhere on Titan, It forms in the upper atmosphere through the action of sunlight on nitrogen and methane, and it falls slowly down to the surface as a kind of organic snow. It builds up on the ground. It accumulates in deposits. It is one of the most abundant solid materials on the Moon, and it is also one of the most polar small molecules in known chemistry, significantly more polar than water itself. Methane and ethane, by contrast, the main components of Titan's lakes and Titan's rains, are among the most non-polar substances you can find. By any reading of the textbook rule, hydrogen cyanide and methane should not interact in any meaningful way. They should slide past each other. They should refuse to combine. They should remain stubbornly separate. The way oil refuses to dissolve in water no matter how long you wait. What the team at Chalmers found, through both the simulations and follow-up laboratory experiments performed at Titan-like temperatures, was that this is not what happens on Titan at all. At those extreme cold temperatures, methane and ethane molecules slip into the crystal lattice of frozen hydrogen cyanide and lock themselves in, forming stable solid structures that combine polar and nonpolar molecules in the same repeating pattern. These structures have a name. They are called co-crystals, and by every textbook rule, they should not form. On Titan, they do. The consequences of this finding reach in two directions at once. Backward, toward Titan itself, the co-crystals give scientists a new toolkit for reading the Moon's surface. Features that Cassini saw in the infrared and could not identify. The strange solid material at the edges of the lakes. The bright deposits where the geology did not predict any, may simply be these mixed solids, sitting quietly in the cold, invisible to a chemistry framework that had nothing in it to recognize what it was looking at. Forward, toward Earth and the question of how life began here. The finding raises a possibility that nobody had quite formulated before. The early Earth had hydrogen cyanide. It had hydrocarbons. It was much warmer than Titan, but it had the same molecules. And the principle that polar and nonpolar substances might cooperate in ways the textbook forbids is exactly the kind of principle that could, if it survives further investigation, rewrite the prebiotic chemistry playbook. The recipe for the very first living things on Earth might have included steps that nobody has been writing down, because nobody knew that those steps were chemically possible. Titan, 440 million miles away, might be quietly demonstrating reactions that mattered for the origin of life on our own planet 4 billion years ago. And Titan is about to be touched, directly, by human technology for the first time in history. Dragonfly, NASA's nuclear-powered rotorcraft, is being assembled right now for a launch in 2028. If the mission holds its current schedule, the spacecraft will arrive in Titan's atmosphere in 2034 and begin flying, hop by hop, across the Moon's surface. It is the first mission ever designed to put scientific instruments directly onto Titan, and the first one that will be able to tell us, at long last, whether the co-crystals predicted in 2025 are actually lying out there in the frozen dark, exactly the way the chemistry says they should be. Dragonfly will sample the chemistry under its own landing feet. It will fly to dozens of locations across the surface. It will, in the most direct way possible, put us in contact with the strangest chemistry in the solar system. But the biggest surprises Saturn has produced in the past 3 years are not actually on Titan. They are on a moon a fraction of its size. A moon that, by every assumption of planetary science, should be a frozen ball of dead ice. A moon that quietly, repeatedly, has refused to play that role. Take a moment with this idea. Saturn is full of moons that turned out to be more than they should have been. The rings turned out to be young. the catalog turned out to be incomplete. The largest moon turned out to maybe not be an ocean world after all. And the smallest of the surprises, the most unlikely candidate, the moon that nobody really expected anything from, turned out to be doing the most interesting thing in the entire solar system. If you have stayed with me this long in the dark, leave a like if it has helped you settle in. The slow journey rewards quiet attention, and a like nudges this kind of patient cosmic content toward the people most likely to enjoy it. I appreciate it more than I can easily say. Now let us meet a moon you could drive across in a single day. Enceladus is small, roughly 500 kilometers across, smaller than the state of Arizona. You could, in principle, drive from one side of it to the other before the day was over. When Cassini first arrived at Saturn in 2004, nobody on the science team expected very much from this little world. The thinking, based on standard planetary science of the time, was that any body this small should have long since cooled and frozen solid all the way through. Heat radiates away from small objects much faster than it does from large ones, the same way a small ice cube melts faster than a large one, except in reverse. By every reasonable model, Enceladus should have been a dead lump of ice in space, geologically inert, frozen since the early days of the solar system. In 2005, Cassini caught it doing something a frozen world should not be able to do. From 4 deep parallel fractures across the moon's south polar region, fractures that the team would later nickname the tiger stripes for the way they ran across the icy surface like the markings on an enormous animal. Enormous plumes of water vapor and ice grains were erupting into space. A moon you could drive across in a day was venting an ocean into the vacuum. The discovery rearranged everything. The Cassini mission, which had been planned for years before launch, was reshaped on the fly to include closer and closer flybys of Enceladus, with the spacecraft pointed directly into the plumes. On the 9th of October, 2008, Cassini made its boldest dive yet. It flew just 21 kilometers above the surface of Enceladus, moving at about 18 kilometers per second, and threaded itself directly through one of the active plumes. Ice particles slammed into an instrument on the spacecraft, called the Cosmic Dust Analyzer. At the speed Cassini was traveling, the grains did not so much land on the instrument as detonate against it. Each particle vaporized on impact, broke into ions, and passed through a mass spectrometer, which read off the precise chemical composition of what each grain had been made of, atom by atom. The data came home to Earth in 2008. And then, in a story that turns out to be common in modern planetary science, it sat in the archive for 17 years. In October of 2025, a team led by Nozer Khawaja at the Free University of Berlin, working with Frank Postberg and several other colleagues, published a reanalysis of that 2008 Cassini data in the journal Nature Astronomy. The team had gone back into the Cosmic Dust Analyzer records, applied modern analysis techniques that had not existed when the original data was collected, and pulled out the chemical signatures of organic molecules that the original team had not been able to fully identify at the time. The list was long: nitrogen-bearing organics, oxygen-bearing organics, precursors to amino acids, the fundamental building blocks, in other words, of the kind of chemistry that life on Earth is made from. Not life itself, not living organisms, but the alphabet from which living organisms might be assembled. The reason this paper matters more than the earlier organic findings from Saturn comes down to timing. Previous detections of organic chemistry around Enceladus had come from ice grains that had been caught in Saturn's wide, faint outer ring, called the E-ring, which is itself fed by the plumes of Enceladus over millions of years. Those grains, by the time they were collected, could be hundreds of years old. And over those centuries, the intense radiation environment around Saturn can chemically weather the molecules in the grains, breaking some apart and cooking new ones into existence that did not exist when the grain originally left the moon. A find in the E-ring is interesting, but it is also ambiguous. You cannot tell whether the chemistry you are seeing is the original chemistry of the ocean inside Enceladus, or something that radiation invented after the fact. The grains that Khawaja and his team analyzed were minutes old, not days, not centuries. Minutes. They had been scooped up by Cassini as the spacecraft dove through the plume itself, 21 kilometers above the surface of Enceladus, before any radiation environment had had any time at all to alter their chemistry. The organic molecules in those grains were not the product of space weathering. They were the actual chemistry of the ocean underneath the ice, lifted up through the fractures in the South Polar region by the eruption of the plume itself, and handed directly to the spacecraft in real time. This is what makes the finding remarkable. We are not looking, here, at chemistry that has been altered. We are looking at the chemistry of an alien ocean, transported to a passing spacecraft within minutes of leaving the source. The second paper came 1 month later, in November of 2025. A team led by Georgina Miles at the Southwest Research Institute, working with Carly Howitt at the University of Oxford, Francis Nimmo at the University of California, Santa Cruz, and Douglas Hemingway at the University of Texas at Austin, published a study in the journal Science Advances that rewrote the question of how much heat Enceladus is actually losing to space. Until that paper, the accepted picture was that, essentially, all of the heat leaking out of Enceladus came out of the South Polar region. The tiger stripes were the vents. The plumes were the visible evidence. Everywhere else on the moon, the assumption was that the surface was quiet, cold, geologically inactive in any measurable way. The South Pole was where the action was. The rest of the moon was just ice. Miles and her team went back to a different Cassini instrument, the composite infrared spectrometer, which had mapped surface temperatures across Enceladus during the mission in the mid-infrared part of the spectrum. They compared two specific sets of observations from the Cassini archive. One set was taken in 2005, when the North Polar region of Enceladus was locked in the deep winter of the moon's long orbit around Saturn. The other set was taken in 2015, when summer had finally returned to the same region. They subtracted out what the sun should have contributed to surface temperatures. They modeled what a passive, geologically lifeless surface ought to look like at those 2 moments, with no internal heat source of its own. And then they compared the model to the data. The North Polar region came in about 7 Kelvin warmer than the passive model predicted. That is a small number that does an enormous amount of work. 7 degrees, in the units astronomers use, is the difference between a surface that is simply cold, lit by the distant sun and otherwise dead, and a surface that is being warmed from below by something internal. Enceladus, it turned out, was not only venting heat through its south, it was also bleeding heat quietly through the north. And not just at the North Pole. The team went on to map the temperatures globally across the whole surface of the moon and found anomalies of internal heat flow appearing in regions that had been thought to be inactive. When they added up the global heat budget, the total came out to roughly 54 gigawatts. That is the amount of heat energy that Enceladus, all by itself, is radiating into space every second. For comparison, a typical mid-sized commercial nuclear power plant on Earth produces about 1 gigawatt of power. Enceladus is putting out the continuous output of 54 such plants. A small, icy moon, the size of a country, is glowing with the energy of a substantial industrial civilization and it has been doing so quietly in the dark for as long as anyone has been watching, and the input matches. This is the part that gives the whole story its weight. Tidal heating models, which calculate how much energy Saturn pumps into Enceladus by gravitationally squeezing it on every orbit, predict an energy input that almost exactly matches the 54 gigawatts going out. The match is not random. Tidal dissipation, which is the technical name for the conversion of orbital energy into internal heat through internal friction, is the engine that maintains the subsurface liquid state of the Moon. Saturn squeezes Enceladus. The squeezing generates heat. The heat keeps the ocean liquid. The ocean leaks up through the fractures. The fractures vent into space. The energy escapes. The cycle continues. That balance is the thing to sit with for a moment. If more heat were coming into Enceladus than was leaving, the ocean inside would eventually boil through the ice, or the ice shell would thin to the point of structural collapse. If more heat were leaving than coming in, the ocean would slowly freeze solid from the bottom up over millions of years. What the data is now showing instead is a system that has been running in a near-perfect equilibrium for what is probably hundreds of millions of years, possibly longer. A liquid ocean held stable by the gravity of the planet it orbits, generation after generation, on timescales that are very long compared to the timescales of biological evolution. In the language of physics, this is what is called a dissipative structure. A system maintained in a state far from thermodynamic equilibrium, not by accumulating energy, but by constantly flowing energy through itself and out into the environment. The Russian-Belgian chemist Ilya Prigogine won a Nobel Prize for showing that dissipative structures of this kind, systems that are driven far from equilibrium by a continuous flow of energy, are precisely the systems most likely to spontaneously generate and sustain complex chemical order. Life on Earth is, in this sense, the most successful dissipative structure we know of. Living organisms exist because energy from the sun flows through them, gets used to build complexity, and then radiates back out into space at a slightly lower temperature. Whether life has found the same opportunity to take hold on Enceladus is not a question the data can answer yet. But the conditions are starting to look stunning. Stable, wet, warm enough, chemically rich, energetically balanced for time spans that exceed almost any other place we know of in the solar system. A moon the size of a small country, a global ocean underneath its ice, fresh organic chemistry lifting out of that ocean through fractures in the south, heat leaking quietly out through the north. The whole system in energy balance, as if someone had tuned it. Cassini has been dead since 2017. The data that proved all of this had been sitting in the archive the entire time, and every paper that has come out in the past 3 years has done the same thing. Found something nobody knew was there, in measurements that had already been taken. There is one more thing above the planet itself that nobody has been able to explain. And in November of 2024, the most powerful telescope humanity has ever launched took 10 hours to look at it, and found things that, even now, nobody can quite account for. Saturn's North Pole is home to a shape that should not be there. A hexagon. 6 sides, each side longer than the diameter of Earth. A 6-sided pattern of swirling cloud and atmospheric flow, locked into place around the planet's pole, holding its geometric form for as long as humans have been able to see it. The hexagon is, technically, a jet stream of atmospheric gas, with winds along its edges moving at around 200 miles per hour. It rotates as a single locked pattern above the pole, while the rest of Saturn's clouds drift past it on their own schedule. It is, by every measurement we can take, the strangest weather pattern in the solar system. Voyager 1 caught the first glimpses of it in 1981, during its rapid flyby of Saturn. When Cassini arrived in 2004 and waited patiently for northern sunlight to return to the polar region in 2009, after the long winter of Saturn's seasonal cycle, the hexagon was still there, unchanged. It had survived almost 3 decades of human absence from any close observation. Today, more than 40 years after Voyager first photographed it, the shape has held. Nothing in our understanding of fluid dynamics fully explains why such a precisely geometric pattern should be stable on a fluid planet for that length of time. The standard answer, if pressed, is that it is the result of a particular interaction between the polar jet stream and the planet's rotation rate. But the standard answer leaves a great deal unexplained. On the 24th of November, 2024, the James Webb Space Telescope spent 10 hours staring at the hexagon. Webb sees in the infrared in wavelengths that Cassini could not reach. The team running the observation, led by Tom Stallard at Northumbria University in the United Kingdom, was particularly interested in the faint emissions coming from the upper atmosphere directly above the hexagon. The ionosphere, the stratosphere, layers hundreds of kilometers above the cloud tops, where Saturn fades slowly into space. Regions of the planet that had been thought of as relatively featureless. The way the air above an Earth thunderstorm is largely empty even when the storm itself is dramatic. What Webb saw was not what anyone had modeled. In the ionosphere, far above the hexagon, the telescope picked up a row of dark, bead-like features strung out across the top of the planet, like punctuation marks across a sentence. In the stratosphere below, an asymmetric, star-shaped pattern of bright and dark structures spread across the polar region. Both patterns sit above the hexagon. Both are separated from each other by huge vertical distances in the atmosphere. And the two patterns appear, as far as the data can tell, to be connected. The darkest beads in the upper layer line up with the strongest arm of the star-shaped pattern in the layer below. The team has been careful about what they are claiming. Stallard, in the press materials accompanying the published paper, said outright that the features were completely unexpected and, at the moment of publication, completely unexplained. Not a soft, polite mystery, a real one. Real enough that the lead author of the paper used the word in the title of his own announcement. The hexagon already had no agreed-upon explanation. And now, above it, at altitudes that were thought to be too featureless to matter, there are structures that nobody predicted, in layers of the atmosphere that nobody knew could hold them. Saturn's North Pole is, in 2026, a vertically stacked mystery. 3 layers of atmosphere, 3 different kinds of structure in each layer, all of them somehow related, none of them fully understood. And this brings us to the place where the story of Saturn, as it stands right now, actually lives. A place that has nothing to do with any single one of these findings. A place that has to do with the pattern of all of them together. Every reversal we have walked through tonight came from data that was already in the archive. Read that sentence slowly. Every single one. The age of the rings was buried in Cassini's final dives in 2017. The 128 new moons were hiding in stacked images from a telescope on Mauna Kea, taken across years and only assembled into discoveries in 2025. Titan's missing ocean was inside the same Doppler signals from 2012 that originally suggested an ocean was there in the first place. The co-crystals on Titan's surface were observable in Cassini infrared lake observations from 2015. The fresh, organic molecules pouring out of Enceladus were collected during a single flyby in 2008. The heat balance at Enceladus's North Pole was visible in temperature maps from the same mission. Cassini has been dead for 8 years. The spacecraft is in pieces somewhere inside Saturn's atmosphere, and the archive it left behind is still being read, for the first time, by people asking questions the original team did not know to ask. The recurring pattern is not incidental. It reflects something fundamental about how knowledge in complex systems builds up over time. The observations are made first. The understanding comes later. Sometimes much later. Sometimes the people who first collected the data are no longer alive when the data is finally read correctly. Cassini's archive is being mined now, not because the data was collected poorly, but because the questions we now know how to ask did not exist when the data was gathered. Every scientific archive is, in this sense, a message from the past to a future that has not yet been imagined. What Cassini recorded is what Cassini was capable of asking. What we find in it now is what we have, since then, learned to look for. This is why dead spacecraft keep producing live discoveries. The scientific value of a mission is not finished when the mission itself ends. It is only beginning. The spacecraft writes the letter. The letter sits in a drawer. Some future scientist, decades later, opens the drawer with new eyes, and the letter says something the original writer never quite knew it was saying. There are plans for going back to Saturn. The European Space Agency has been studying a mission concept dedicated to Enceladus for the 2040s, designed specifically to fly through the plumes the way Cassini did, but with instruments built this time to look for biological signatures rather than to stumble on them by accident. Dragonfly, the rotorcraft built for Titan, is already being assembled, scheduled for launch in 2028 and landing on Titan in 2034. If both missions hold their schedules, the 2040s could be the decade Saturn's moons are touched directly for the first time in a generation, and possibly the decade in which the question of life on those moons finally gets a partial answer. None of that will arrive quickly. The distances are enormous. The time between launch and arrival is measured in years. The patience required is the patience of the planet itself, which has been doing what it does for 4.5 billion years and is in no particular hurry to explain itself to us. In the meantime, the system continues. The rings are tilting slowly back into view, year by year, as the angle between Earth and Saturn rotates and the foil-thin structure becomes once again visible from our position in the sky. By 2027, the rings will be fully reopened, displaying themselves in the full glory of every textbook illustration. The hexagon will continue to hold its impossible geometric shape, while Saturn's clouds drift past it. The ocean under Enceladus will continue to leak out through the tiger stripes, throwing organic chemistry into the vacuum, where some of it will eventually settle into the E-ring, and some of it will be lost forever to deep space. The slush layer inside Titan will continue to sit just at the edge of melting, with its scattered pockets of warm water, waiting for a spacecraft to come and ask what it is. And somewhere in the thousands of hours of Cassini data still unanalyzed, in measurements that have not yet been looked at carefully, in instrument readings that have not yet been compared to the right physical models, the next reversal is already there. Already recorded, already waiting for someone, possibly years from now, possibly someone who is currently in elementary school and does not yet know what astronomy is, to go back and find it. Saturn was never a still picture. It only looked like one because nobody had looked for long enough, or carefully enough, or with the right kind of eyes. The rings did not really vanish on the 23rd of March, 2025. They were only turned to one of the angles where a planet hides what it is made of, and every other angle, it turns out, has been hiding something too. Take a breath here. Let the size of all of this sit with you. We live on a small, wet planet, in a quiet corner of an ordinary spiral galaxy, in a universe full of objects so much older and stranger than us that the comparison is almost embarrassing. And yet we have managed, from this small, wet planet, to send a single robot to a planet over 1 billion miles away, leave the robot in orbit for 13 years, collect more data than any human team could process in a lifetime, and then, after the robot is dead and the mission is over, continue to find new things in its records year after year. Saturn is not quiet. Saturn was never quiet. We just had to slow down enough to hear it. There is a kind of calm that comes from realizing this. The universe is not finished surprising us. The data we already have contains discoveries we have not made yet. The instruments we have already launched will continue to teach us new things long after they have stopped working. The way a letter from a grandparent can still arrive in your life decades after they wrote it. None of this depends on the next mission. None of it requires the next $1 billion of hardware. The most exciting findings of 2025 did not come from any new technology. They came from people sitting at desks, going back through old data, asking better questions than the people who first collected it. That is, in its own quiet way, a kind of comfort. The universe keeps its secrets close, but it does not keep them forever. They come out slowly, patiently, year after year, in papers nobody outside of a small group of specialists ever reads, in data sets that nobody outside of 1 or 2 universities has ever heard of, until eventually one of those papers crosses some threshold and the news of the discovery escapes the academy and reaches the rest of us. And we, sitting in the dark, listening, get to feel for a moment what it is like to learn something the universe had been hiding in plain sight. If you have stayed with me all the way to the end of this journey, thank you. There is something quietly wonderful about choosing to spend an evening with the slow, patient news of a planet 1 billion miles away, instead of with everything closer and more urgent. It says something about you. It says you can sit with scale. It says you can let your imagination travel. It says you trust the dark to hand you something worth holding on to, if you are willing to wait for it. If you would like more journeys like this, the kind that take their time, the kind that let you drift, the kind that pay attention to the slow and the strange instead of the loud and the new, you already know where to find them. Subscribe if you have not yet. Drop a comment telling me which of tonight's revelations hit hardest. I read them, and the comments are sometimes more interesting than the videos. And if any of this stuck with you, share it with someone who would also like to fall asleep to a planet quietly rewriting its own biography. Until next time, keep your eyes on the dark places. The universe has more secrets in the empty corners than it has in the bright ones. And somewhere out there, right now, in an archive that nobody has fully opened yet, in a data set that has been sitting on a hard drive for 15 years, in measurements that the original team did not know how to interpret, the next great revision of our understanding is already there, already complete, already waiting. Sleep well, if that is what you came here for. Dream of a small bare planet on a March night, briefly without its crown. Dream of a moon the size of a country, glowing quietly in the dark with the energy of an industrial civilization. Dream of a chemistry textbook that turned out to be wrong about a moon 400 million miles away. Dream of a hexagon the size of a continent, holding its shape for 40 years while every other cloud on the planet drifts past it. Dream of 15-hour delays and slush layers and crystal lattices that should not exist. The dark is patient. The dark holds its mysteries until we are ready for them. Saturn has been holding its mysteries for 4 billion years, and as it turns out, We are only now starting to be ready. Good night, and welcome to the deep, slow news of the outer solar system, where the rings are younger than the dinosaurs. The moons are the wreckage of older moons. The largest moon may not have an ocean. The smallest active moon is glowing with chemistry that looks like life. And somewhere above the planet's north pole, 3 layers of atmosphere are holding hands in patterns that nobody, yet, can explain. The story is not over. The story is still being written, in archives we have not yet opened, in data we have not yet read, in papers that have not yet been published, by scientists who are right now, somewhere on this small blue planet, sitting at desks, asking better questions than anyone has thought to ask before. We will be here. The dark will be here. And Saturn, whatever it really is, will keep doing what it has been doing, slowly, patiently, in the cold beyond Jupiter, waiting for the next set of eyes to catch the next reversal. Whenever you are ready. The dark keeps its appointments. Good night from the rings and the moons and the cold places and the slow story of a planet that is, every time we look, more interesting than we had quite been ready for.